Sometimes we have functions that we cannot approach with the product rule or the quotient rule, and they're not trig identities, and so we need another way to approach them that's just too complicated. And one approach we can take is using what's called the chain rule. And maybe in words, I would say the chain rule is something like this. The derivative of the whole thing times the derivative of the inside. Right, we have a composite function. So for example, if we had a function like x squared, well, that's easy to take the derivative of. Right? We can just use the power rule, and it's 2x. But what if x equaled y to the 5th plus 1? How are we going to take the derivative if f is now y to the 5th plus 1 squared? And the issue is that things change because now we have a composite function to deal with. And so the process is to take the derivative of the whole thing. Right? F prime would be equal to 2 times y to the 5th plus 1. And that portion is no different than what we did here using the power rule. But we also have to account for the inside. And the derivative of the inside, y 5th plus 1, is equal to 5y. And this would be the expression for the derivative of this more complicated function. Now we could get the derivative of f by using the product rule, because we could write this as y to the 5th plus 1 times y to the 5th plus 1. And by the product rule, this would be the derivative of the first, so 5y to the 4th, times the second function, plus the first function times the derivative of the second, 5y to the 4th. And so these are actually equivalent expressions, because if we factor, this should be 5y to the 4th. If we factor out 5y to the 4th, we would have left y to the 5th plus 1 times y to the 5th plus 1, which is equivalent to 2 times y to the 5th plus 1. So they're equal. The chain rule works. Right? In general, the rule can be expressed something like this. Right? Your textbook explains it. It has a proposition this way. We want to take the derivative of, if we want to take the derivative of a function, we'll say that function is g to the x, and it's g to the x to the n, right? So it's a function to some power, and its derivative would be, we drop the power, n, decrease it by 1, so n minus 1, times g prime of x. I've always found it easier to think of it in terms of finding the derivative of the whole thing times the derivative of the inside. Let's look at y equals tangent cubed of x, which is the same thing as tangent x quantity cubed. Well, what would y prime be? Well, y prime would be the derivative of the whole thing, so 3 times the tangent of x times the derivative of the inside. What's the derivative of tangent x? It is secant squared x, using the chain rule. And then we could have problems where we're using all sorts of different things. Another expression for the chain rule is if you want to take the derivative of a composite function, so we could say it this way, f of g of x. Well, first we're going to take the derivative of f, which happens to have g of x as its input. And we're going to multiply that by the derivative of g. But again, it's the derivative of the whole thing times the derivative of the inside. Let's try another one. Let's say we're working with y equals 9x cubed plus 1 squared times the sine of 5x. Well, this is a product of two functions, so I'm going to use the product rule. And by the product rule, I need to take the derivative of u in this case, which is 9x cubed plus 1 squared. So by the chain rule, the derivative of u is 2, dropping the power, times 9x cubed plus 1 to the first, times the derivative of the inside, which would be 27x squared. And by the product rule, this will be times v, so times the sine of 5x plus the first function, which is 9x cubed plus 1 squared, times the derivative of the second function. Well, the second function, v, is sine of 5x. The derivative of the whole thing would be cosine of 5x times the derivative of the inside. The inside is 5x, so I need to multiply by 5. And this huge expression is my quantity. We could simplify this if we wanted to. This is acceptable to leave it this way as well. So we have the chain rule as a way to deal with complex functions.